Okay, so we're going to talk a little bit more on position time graphs. By now, you can recognize a data table like this. You know that this is going to be linear data because of the gaps in the left-hand column, which is the dependent variable on the y-axis. The gaps in the left-hand column are the same for every second. And these are the gaps in position. So the variable on the left-hand side, the dependent variable, that goes on the y-axis. So we understand that if we were to take this data table and graph it, it looks something like this. Time in seconds, position in centimeters, that's our normal division because we're using meter sticks and we're seeing all the groups of tens of centimeters, so it goes up to 100 centimeters. So we're usually going to be marking our positions in centimeters. So we graph this 0, 0, 3, 6, 9, 12, 2, 3, 4, 5. And it doesn't have to be perfect, but try to plot the points best we can. Three at 9, 12 at 4. Not forget the 15, 5. And so at this point, we just draw a best fit line of best fit, however you want to designate that. This line here, of course, we can take the slope of this line, and that's going to give us the average velocity. So this line of best fit represents not the slope necessarily, we can take the slope of that line. That line of best fit tells us about the average velocity. Once we take the slope, that basically tells us what the average velocity is going to be, because the average velocity is the rise over run, which is change of position over change in time, very similar to m equals delta y over delta x, where of course this is the y-axis. And times in the x. Just imagine, if you will, back in your algebra classes where this is just y with arbitrary numbers, and this is x. But in physics, this is going to be a position versus time graph from a position versus time data table. So that's the subject of today, position time graphs. And we're going to take a look at a couple of examples of different position time graphs and how we can translate those graphs into what we call motion maps. And that's going to be part of the last bit of our constant velocity particle model project that we've been working on. So let's take a deeper look at this. So again, dependent variable, the left-hand column, we know that's the position for this type of graph, the position versus time. It's the independent, our numbers, okay? Now, if we wanted to pick this graph into what we call a motion map, which is going to be what we're going to see in the CVPM on page 4. Well, the motion map can be represented in different ways, but the one on page 4 has this look and feel like this. So these markings here are going to all be positions. So if you want to just make this into centimeters, in this case, meters, centimeters, whatever unit of displacement we're going to use. 1, 2, 3, 4, 5. Well, I'm representing that in terms of seconds. Let's do it in terms of the positions that we have. So it's going to be 3, 6, 9, 12, 15. So all a motion map is we're trying to show the viewer where the object is after every second. And each second is going to be represented by an arrow. And then we can, put a dot after 1 second or after 2 or whatever the time units are. In our case, it's going to be 1, 2, 3, 4, 5. So it's going to be every second. So after the first second, we draw an arrow at 3 because we see, at least from the data table, after the first second, we're at 3 centimeters. After the second, 6, and so on. It's pretty uniform. So the arrow, use a different color, I guess. The arrow will look like this. So if you want to say that, this line here is 0, we can start from 0 and go to the 3 position, the 3 centimeter position. Draw the arrow at that point, put a dot if you wish, or just leave it as an arrow. We know that this represents 1 second. After 1 second, he's at 3 centimeters. And after 2 seconds, he's at 6. After 3 seconds, and so forth. It's pretty uniform. 3 centimeters every second. This is another way of depicting your velocity, which is your displacement over time. Every second, he covers 3 centimeters, and it's pretty constant. 4th second, he's at 12. And after 5 seconds, he's at 15. So another way of showing the uniformity of that slope, which is your velocity really. And this kind of, leads into my general statement that the slope of a position time graph. So this is a position time graph. The slope of this position time graph gives you the average velocity. That slope doesn't change. As we see here in the motion map, at least depicted by the time intervals doesn't change. The amount of position every second, or the change of position every second, doesn't change. It stays the same at 3 centimeters every second. So this is another way of depicting your average velocity, which is 3 centimeters per second. So again, all the motion map is you have the positions down here in black, and then you're telling the viewer, communicating in another way where the object's going to be after every second, or after every 2 seconds, or whatever the time divisions are. Okay, so let's go on to another example. So you're going to be, looking at that in the CDPM, and we'll be, of course, looking at that together. And filling in that page. Okay, so another type of position time graph we're going to see is one. Let's see, we have, let's draw it arbitrarily, TX. And so we have one best fit line going like this, and then we have another one starting at some y-intercept, the y-intercept being a position. And let's say that this is line A, line B. Again, these are best fit lines through data points. I have to draw the data points or plot them down, but we understand that these are best fit lines through some arbitrary data points. And you're gonna have questions like, okay, which object starts at a higher position, or where or when do the objects meet? Let's say we have some arbitrary time unit here. Let's say this is 0. Let's say this is 1, 2. So we'll see that in our project. So example, like, so one question is like, which object starts ahead of the other? Well, we can clearly see that object B starts ahead, because if these are positions, and they are, well, object B is going to have, that's, yeah, it doesn't matter what this is going to be, 2 or 200. We know it's going to be ahead of A because A starts at 0 and B is going to start at some positive non-zero number. And obviously, this domain, this part of the positions above the x-axis are going to be positive, and they're going to be always pointing towards the east. So if we go down here, you know, below the 0, below the x-axis is negative numbers. It's like, you know, like your plus minus numbers on the y-axis, right? So these numbers are going to be negative. These positions are going to be negative, and this represents west. I know it's upside down, but you know, north south. Well, remember, this is the x-axis. We're doing position on the x-axis versus time. If we did on the y-axis, it'd be y versus t. It'd still be position, but in the vertical axis. We just have to always be aware of our frame of reference. Where are we depicting these positions? These positions are going to be depicted east-west, and that's been our paradigm so far. We've been having the cart go east to west. We've been on flat surfaces. We haven't gone in the air yet, dropping balls, throwing them in the air, and the acceleration being the acceleration due to gravity. So this is the position along the x-axis, even though represented by x. X is the common symbol for position, but this, you know, is indeed horizontal on the x-axis. We are depicting time on the x-axis here just by convention, but remember, these positions are horizontal, east-west. So that's our graph, and here's basically our position in real space. So this would be 0, 1, 2, 3, 4, 5, typical east. This would be -1, -2, -3, -4, -5, right? And this would be west. Obviously, as we said in our very first lecture on one-dimensional motion, these are positives. The east, west, negative. It's all the number line. We're just representing the number line into real things, into real quantities. That's all it is. We just have to extend our imagination up to the number line being directions. The plus and minus signs actually represent directions. In this case, the directions are east and west. So, so back to this, right? Which object starts ahead of the other? Object B. When do the objects meet? So basically, when do they have the same position? Well, it would be at 2 seconds. So kind of just easy questions. Kind of look at the graph and answer some questions about that, which is what we're going to be doing tomorrow. Let's see, anything else? I guess next thing we can just cover when we talk about the CVPM in detail. But I just wanted to do more on position time graphs. So the more we do this early now, then when we go to acceleration, hopefully there's a lot more familiarity with translating data in a data table to a graph and even to a motion map, you know, if necessary. So it's just all different ways as scientists, we are yearning to depict our data in, you know, a variety of ways. Data table, data in a graph. We understand the slope here. The slope of a position time graph gives us the average velocity, which is change in y over change in x. But we know that the y-axis has position, so change of position divided by change in time interval. So these are real quantities now, not arbitrary y and x, rise over run. They mean something real. So this is displacement over time interval. We know that the displacement is delta x, final position minus initial position. So velocity is displacement over time. So it behooves us to really become comfortable with the definitions, our frame of reference, what kind of data we're looking at. Is it linear, nonlinear? In this case, very linear, very easy. We've also talked about standard deviation, how these data points could fluctuate above or below the mean or the average. The average in this case is not some arbitrary average, it's an average velocity. So we know that that plus minus signs means, oh, I'm fluctuating on this side, it'd be the plus side, and below it be the minus side. Again, you know, old hats, the dependent variable goes in the left-hand column, which is the position in this case, and the independent variable is time. Time will always be the independent variable. So don't confuse it with domain range so much. It's definitely like that, but we just always need to be aware of what we're depicting. Just because you've seen domain range and x-axis quantities on the left-hand side and the range quantities on the right-hand side, don't confuse it and say, okay, I'm gonna put time on the left-hand column and then x on the right-hand column, and then have time in the y-axis, because you know that that's dependent or domain. Always just check yourself, all right? I'm just trying to give you a framework, and notice that conventionally positions are left-hand side, time is right-hand side. But if you do it the other way, make sure that you just put time in the x-axis and position in the y-axis, or else your slope will, you have a negative slope, and then that just kind of ruins it. So always be aware. Motion maps, where is the object after every second? These numbers represent the positions. And we know after the first second's at 3, and then it changes position. It changes 3 centimeters every second. That's what the red arrows represent. After every second, 3 more centimeters. First second, 3. Second second, 6. Third second, 9. Fourth second, 12. 5 second, 15. And you can predict, okay, at position 18, it's going to be there after the 6th second. Now, it's always divisions of 3 in this case. All right, and then these best fit lines of position versus time, or velocities really, you can use this to answer certain questions like, okay, which object starts ahead of the other one? We said object B. When did they actually meet? They meet at 2 seconds. We can even answer questions like which object is actually moving faster than the other one. And, we'll be answering that in our CVPM. So I'll tell you right now in this video that object A is actually moving faster than B. How do we know that? You might ask me, how do we know that, Mr. Kelly? Because the slope of A is greater than the slope of B. And I will say this again, that when we are aware of what we're looking at, okay? We're aware we're looking at a position versus time graph, and then we know that the slope of a position time graph gives us the velocity. If the slope here, or since the slope of A is larger than the slope of B, that means that the velocity of A is greater than the velocity of B. Therefore, object A is moving faster than B. You just look at the slopes. That's all it is. Slopes in arbitrary or abstract algebra, right? Now you're translating that same logic. You're translating and even transforming it, really, the same logic into some real quantities. Instead of saying slope and equation of line, we have functions. Instead of equation of line, we just say functions. and slopes become velocities in this case. In other cases, slopes can become accelerations, or forces, let's see, the forces, which is about position versus, or momentum versus time graph, for example. So we always have to be aware of what we're looking at, what kind of data that we have, as in position versus time or force versus displacement. What kind of data is it? Is it linear? Is it nonlinear? So these are the tricks. We need to have these tricks. We need to have these establish these ground rules before in kinematics, or just one-dimensional motion, position versus time, before we go to energy versus time, or momentum versus time, force versus displacement. It's going to be the same logic, but we have to have the tools right now so we can translate it to different physics or different physical phenomena. So it's very, very important. So again, number line, east plus, west minus. Hopefully we're latching on to that. And yeah, so that'll basically do it for the last bit on more on position time graphs. All right. Talk to you later.